Um, was anybody successful after our conversation yesterday? After me giving you guys hints, were you guys able to come up with anything?
No.
No. Um, okay. So what I'm gonna do, okay, with this problem, and I'm not saying that this is like the only way to do it, but this is a practical way, at least for myself, okay, um, to do this. Okay, there was a strategy that was suggested yesterday, which was to find the area of the parallelogram, like the overall large parallelogram, and then subtract it by the area of the four circles to get the area in between. That is definitely a strategy. However, I'm not going to approach it that way. And the reason is, um, well, I think in this problem here, I want to demonstrate to you guys, um, it's it's always a good idea to think outside the box. It's always a good idea to try to make connections. So I want to approach it by drawing all over this, okay, and to show you guys that there are other geometrical relationships, okay, that is underneath this, right? So yesterday during the office hours, I spoken with you guys that was not recorded, okay, and I told you guys this, right? Make these connections here. And by doing this, we immediately see that there are other types of geometries that result from this. Okay, there are a whole lot of other smaller figures that are readily recognizable. And this kind of like technique, this kind of skill, I would say is universal for any kind of like problem solving. Anytime you don't know something, it is the your advantage, okay, to draw all over it and to see and make other connections. Okay. So if I break this thing up in this manner here, I'm gonna for those of you who are watching this recording at a later point, I encourage you to like pause and think about um, how many different types of triangles we have here and whether or not certain triangles are congruent to one another. Okay, and then from there, try to justify how we can find the area of all those different triangles. Okay, and there was one fact, okay, that I had shared with you guys in the Google Doc, and that was a line tangent to the circle, right? So like I have here, okay, a line tangent to a circle. What angle is formed between the tangent line and the radius again?
90 degrees.
It was 90 degrees. That's right.
90.
So again, at this point, okay, those who are watching this recording at a later point, I would encourage you to try to figure out, okay, whether or not these triangles here are in fact the same, okay? All right, whether or not these triangles over here, okay, are in fact the same or not, okay, and try to articulate for yourselves. So yesterday, those who remained in the office hours, I went over with you guys. Do you guys remember what the articulation was, or why the triangles that was in pink before, why are they the same? Do you guys remember how that came about?
The hypotenuse leg.
It had to do with using the theorem hypotenuse leg. That's right. So actually, this angle right here, okay, is 90 degrees, right? And this angle here is 90 degrees. And Sasha, you said yesterday immediately that this quadrilateral is what kind of quadrilateral?
A rectangle.
It must be a rectangle. That's right. Okay, because of the fact that we have right angles in there. Okay, and the two sides over here they all measure r. Okay, so we have that that understanding that it's a rectangle. So therefore, this angle over here must also be a right angle. Okay, these two triangles over here, this triangle in pink must be the same as this triangle in pink, right? Why again?
Hypotenuse leg.
That was because of hypotenuse leg, because this side here, being the hypotenuse, right, is shared between the two triangles, and the legs, okay, they both measure r. So therefore, those two triangles must be congruent. Okay, so if that's the case, then therefore, these two angles over here must be the same or different again? They must be the same. Okay, and then this angle over here must be a right angle because we have a rectangle over here. This guy over here is a rectangle, right? This guy's a rectangle. Which then just leaves us with this guy over here. This guy over here. Okay, that angle over there. And we want to establish whether or not, well, should this angle here, and we don't know whether or not this angle is the same as the other two, okay? Because right now that was not established yet. But one thing we do know is, what kind of triangle is this?
Equilateral.
It's equilateral, right? So if that's equilateral, what must be the angle measure of this guy of this guy right here?
60.
That must be 60. Okay, so 60, I have 90, and I have 90, and these two angles over here are the same. What must be those two angles then?
30.
60.
No, not
60,
quite.
60,
60.
It must be 60, 60. That's right. Morning, Ty.
20.
So those two angles must be 60. Okay, so this is 60, and this is 60. So
Oh, yeah, because 60, yeah, okay.
say that again.
No, I was hanging, but yeah, we're good.
Oh, okay. So wait a minute. I have 60. So all those angles are the same, and I want to try to color code this. Okay, so I have this angle over here is the same, this angle over here is the same, and this angle over here is the same. Okay, and I want to color code this right here. That what I just highlighted in green there. What's the measure of that angle?
90.
90.
90. This must be also how much?
90.
90. This, okay, because this line, okay, cuts right down the middle of the equilateral triangle, okay, that angle in green here must also be how much?
90.
Must also be 90. That's right. You guys are so good here. Right? That must be 90. Okay, so we have two. That means we have two angles. And one last thing that is in yellow, okay? This segment that I am highlighting in yellow right now, what's that length?
R.
180.
R. This is R, and that's R. So all of these triangles, okay, must be congruent because of angle, side, angle, okay? All those angles must be congruent because of angle, side, angle. So if that's the case, okay, I'm going to take a step back, and I'm going to erase this. And so wait a minute. That means what's happening here is these triangles that I have unintentionally erased, these triangles here, okay, that I'm highlighting in pink, are all going to be the same. All of these are going to be the same. All of these triangles are therefore congruent, and I am going to highlight that in pink. All right. And same thing goes for this. All of these are going to be the same because of the mere fact that, you know, this is symmetrical here. So all those triangles are going to be the same, okay? And we can actually go through the same process and try to prove why these triangles here are all the same. But it's the same logic, right? That these smaller triangles are also going to be the same, which I'm going to color code in green, okay? We're all good with this? And I'm going to do one more thing, and that is in yellow, okay? I am going to highlight this and call these the area of those rectangles there in yellow. So really, essentially, all the area of the entire quadrilateral, of the entire parallelogram here, is made up of 3 different types of areas. Can we all recognize this? There's only 3 types of areas here, right? There's an area that's in pink, an area that's in green, and an area that's in yellow. We're cool? All right. So I want to start off by doing the easiest one. Yellow. What's the area in yellow?
360.
Times I.
Not 360. I'm talking about the area now, right? What's the area in yellow?
It's
The Pythagorean.
it's
R
2r squared.
plus 2r squared.
It's base times height. It's 2r squared. It's 2r squared.
Wait, don't you have to divide it by 2?
Say that again.
Never mind.
Right? The area of the rectangles are 2r squared. And if you're having difficulty recognizing this or seeing this, okay, what's the height? When I say height, I mean what is the length of this guy? You see what I'm highlighting right now in blue?
Yeah.
Guys, that's r, right? What is this length going diagonally like that? Whoops. Hold on.
R squared. I mean 2r.
It's 2r. This is 2r, right? So therefore, okay, so therefore the area of the rectangle is 2r squared, okay? I'm glad we are in agreement there. Whoops, I did not mean to do that. Oops. Okay, so the area is 2r squared. Whoops. Now let's try to figure out the area that's in pink. Okay, so the area in pink. Okay, let's try to figure that out. What is and for this I'm going to draw the triangle. Okay, so that I have this triangle like that. Okay, so I know that the base of the triangle, right? The base of the triangle. And what I'm going to do is I'm going to focus on this guy right here. You guys see what I'm highlighting right now?
Yeah.
Okay, what's that length?
That's R.
That is R. Okay, so therefore this is R. Okay. What is the length going in this direction? Do you guys see what I'm highlighting?
That is
2r.
That is 2r. That's right. So that's 2r. Whoops. So that's 2r. And this is a right triangle, is it not?
Yes.
So how can I figure out what this guy is?
The Pythagorean theorem.
Pythagorean theorem. Okay, so what would that be? So let's see here. I don't know what that is. Let's call that h or something, right?
H squared plus r squared equals 2r squared.
So it could be like h squared plus r squared.
We got to enclose 2r in parentheses, though, right? Because we're squaring the entire length of 2r. If I do this, okay, let's look at the thing that's in parentheses there, 2r quantity squared. Okay, what is that? If I square 2r, it's going to be
4r squared.
r squared, right? Because it's 2r times 2r. And I have h squared plus r squared is equal to 4r squared. I'm going to subtract both sides by r squared. And if I do, I'll end up with h squared is equal to how much?
3r squared.
3r squared.
3r squared. And with that, I'm going to take the square root of both sides. Is there anything that I can do to pull? Is there anything that I can pull out of the square root?
You can make it
Squared.
radical 3r.
Yeah, because r squared is a perfect square. So that gets to come out of the square root. R squared is a perfect square. 3, on the other hand, is not a perfect square. So the 3 must remain in the square root. So what exactly is h? H is equal to r
Radical 3.
radical 3.
Radical 3.
Okay, so that's what h is. We haven't finished it yet, okay, but that's what h is, and that's important here. How do I find the area of a triangle, of a pink triangle?
1/2.
You need to multiply h times r.
It's 1/2.
1/2 base times.
That's right. Times h, base times height. What's the length of the base one more time?
R.
R. And
R.
then times r radical 3.
R radical 3. Or
And I can from this I can combine things together, right? R and R makes how much?
2
R squared.
R squared. I have 1/2 times radical 3. Well, 1/2 times radical 3 is simply radical 3 over 2. Okay, so the area, okay, of the pink triangles, okay, is radical 3 over 2 r squared. Lovely. So we're almost there, okay? What we're going to do next, okay, is we're going to focus on the last area, which is the area that's in green. That's this stuff right here, right? And with this, I'm going to do a little bit more articulation. Can we all agree that this angle over here is 90? Are we in agreement there? Yes?
Yeah.
Yeah.
Are we in agreement that this angle is also 90?
Mhm.
All right. What's this angle over here?
30.
That is indeed 30. And what is this here?
Also
30.
30.
Very nice. What's this here?
60.
60.
60.
Love that. You guys are so good. You guys are so good. All right. And these two angles over here must be the same because the two triangles that are in green, okay, are congruent, right? So what must be those angle measures?
30.
30.
Also 30.
Love that. They must be 30 apiece. Okay. And again, I have 90. And this guy down here must be 60 then, yes?
Mhm.
I'm dealing with
Yeah.
another 30, 60, 90 triangle. All right. So with that said, what I'm going to do, and this is something that you guys had studied like maybe 3 weeks ago, okay? 3 to 4 weeks ago. We're dealing with 30, 60, 90 triangle. Okay. And this was one of those like special right triangles. Do you guys remember that? And these special right triangles will always share
1/2.
A ratio.
those corresponding ratios. Do you guys remember that?
Yes.
Yes.
Or another way of thinking about it, is it will look like this: 60, 30, 1/2. And I think Sasha was mumbling this, right? This is 1/2. This is square root of 3 over 2. And what's the length of the hypotenuse, Sasha?
1.
That's right.
1.
1.
So these are all the same, okay? It will always share that kind of ratio, okay? All right, so now with that said, all right, so we're dealing with the triangle that's in green right now, right? Okay, so if we're dealing with the triangle that's in green, okay, if I'm trying to find out what the area of the green triangle is, okay, at the moment, do I know what the height of the green triangle is? Do I know what is the height of the green triangle? What's the height of the green triangle?
R.
It is indeed r. That's right. That's r. Okay? I need to know what is that going to be. Okay? So what am I going to do? Well, Sasha, can you give me a letter for the question mark there?
I S. I don't know.
X? Okay.
Yeah.
So Sasha, right? X
Yeah.
over R, right? X over R will equal to what? How can I set up a proportion to figure this out?
I'm not sure.
Not sure? Anybody know? So X over R. X corresponds with 1, doesn't it?
Mm-hmm.
Oh,
And
oh,
R corresponds with
1 over
radical 3, doesn't it?
radical. Yeah.
So what am I going to write on the other side of that fraction?
1 over 1/2 over radical 3 over 2.
1/2 over radical 3 over 2, or 1 over
over
radical
square
3, right?
3.
Is my screen refreshing, guys?
Yeah.
No.
It's not. Okay, so give me a second. I want to back out. Hold on. Is my tablet coming up?
Not.
Do you guys see my tablet or no?
Nothing yet.
I see
Nothing. Nothing yet? Technology. It's great when it works. It's terrible when it doesn't. And especially when you're dependent on it.
It's great, but it.
Here we go. Now it's refreshing. Okay.
No, just now I see.
All right, so that's the relationship that we have right now. We have X over R is equal to 1 over radical 3. Cool? Okay. We need to find out what is the length of that base, okay, to find out what is the area of that green triangle, right? So wait, having said this, okay, X therefore, if I multiply both sides by R, okay, and leave the radical 3 there, I'm going to be left with X is equal to R over radical 3. Everyone okay with that? Okay. Now, just one thing though. Remember, there's this rule, okay, that Regents courses, okay, expect you to apply. SAT courses expect you to apply, but in the real math world, it's not really that big of a deal. But there's this concept called rationalization. Okay, do you remember what that is?
Yeah, radicals can't be on the denominator.
That's right. The radicals can't be in the denominator. So in order for us to get rid of those radicals in the denominator, okay, what do?
We multiply both by the radical itself.
That's right. So if I multiply top and bottom by radical 3 over radical 3, I'm going to be left with R radical 3 over well, radical 3 times radical 3, that's just 3. Okay, so that's how I get rid of it. So X is equal to R radical 3 over 3. And we're almost done, okay? We're almost done with this. So now that I know this, okay, X is equal to R radical 3 over 3. I'm going to get back over here because this is where I am summarizing all of this stuff, okay? What is the area that's in green? What's the area in green now?
1/2 R times R radical 3 over 3 squared.
That's it.
Or just...
And I can actually combine things together, right? R and R makes how much?
2R.
R squared, right? And the 2 and 3 gets me 6. So I'm left with radical 3 over 6
R
times r squared. Okay? So that's the area of the stuff that's in green. Okay. So now that I have this, okay, I have all the 3 basic areas now. Okay? And what I got to do is account for all of this. Okay? So to account for all of these areas, okay, how many pink areas do I have?
Yes.
8.
8.
I indeed have 8. So the total area of the parallelogram, okay, is 8 times r squared radical 2 r. I'm sorry, radical 3 over 2 r squared. That's the area in pink. All the area in pink. Whoops. What is the area in green? All the area in green?
4.
I have 4 of them. So 4. Okay, r squared, radical 3 over 6 r squared. And how many yellows?
4.
I have 4
4.
yellows.
So it would be 8r squared.
That's right. Okay, and we're really like 80% done now. Okay, when I say 80, that's because we still have like one other minor step here. So I'm gonna, is there anything that I can do to maybe possibly simplify this stuff? You guys see here that I have the 8 and a 2, right? 2 goes inside of 8 how many times?
4.
4.
4. So I have 4
4.
radical 3r squared plus the 4 and 6, okay? How many, what's the common factor between 4 and 6?
2.
2.
2. So I'm left with 2 radical 3 over 3 plus, and then I can combine the 4 and 2 like Ty was saying a moment ago. So this is really 8
8.
r squared. And we're almost there, okay? We can combine, can we combine any of this stuff together? Not exactly, but you know what? It would be more confusing if we did anything else. So I'm just going to leave it like that, okay? So that is the area of the overall quadrilateral, okay? But what are we supposed to do with this? Because I'm trying to find out the area of the blue region, right? So at this moment now, because we found the area of the entire quadrilateral, I'm going to erase everything here.
You need to find the circle and then you'll
Oh.
subtract that.
I need to find the area of the blue, right?
Can you subtract 4 pi r squared from it?
That's right. So right now, I'm going to take this thing and subtract it by 4 pi r squared. And ladies and gentlemen, this right here is our final answer. This guy right there.
Could we combine all the r squareds?
You can. And actually, what you can do to make this thing look a little nicer, okay? You know how like in English class, who's your English teacher again?
Miss Rosen and
Miss Rosen?
Miss Rosen. Okay, so you know probably Miss Rosen would say this, or I don't know if she would. Very likely she would. Okay, you have a great idea, but it's the execution, right? And it's how you're conveying it. Okay, that's like mumbled and jumbled. Okay, so same thing goes in mathematics. That thing that I have boxed in there right now, okay, that's the answer, that's the idea, but the conveying of the idea is very mumbled and jumbled, isn't it? It looks really like complicated. So
Like you could make, I know you could combine the first 2 and then make that 14 radical 3 over 3
right.
2r.
We can try to combine, okay, this stuff together, okay? So in order for me to do this, okay, let me just do this really quickly here. I can create common denominators, okay, between this guy and this guy. This guy, okay? So notice right now, the fraction in the middle has a denominator of how much?
3.
3.
3. So I want to multiply the first term here by how much? 3. So I'm left with 12 over 3. Do I need to multiply the second term by anything?
No.
Do I need to multiply the last term by anything?
Yeah. 3.
No.
Three.
What do I multiply by? So it's 24 r squared over, okay?
Right.
And if I look at this, okay, between the first two terms now, okay, or actually all of these, if I were to combine them all together, okay, I'm left with, well, 12 radical 3 and 2 radical 3. What will that give me?
14 radical.
That'll be 14 radical 3.
That indeed will be 14 radical 3. All over 3, okay? And then minus 4 pi r squared. And to make this look even nicer, to make this thing look even nicer, okay? Bear with me for another moment, okay? Do you guys see that there's a common factor here?
R squared.
Yeah, r squared.
I can factor that out. This is going really above and beyond now, okay? So I have 14 radical 3 plus 24 over 3 minus 4 pi times r squared. Okay? And we can make it look even nicer. Okay? I can create a common denominator here. What do I multiply 4 pi by to create common denominators?
3.
3 over 3. That's right. So I'm left with
12 pi over.
at last, 14 radical 3 plus 24 minus 12 pi, right? Because I'm multiplying 4 pi by 3 over 3. And it's all divided by 3. And this, ladies and gentlemen, is a very concise answer that Miss Rosen would accept as a final
I
statement.
think you make it even more concise.
You think you can make it even more concise?
Yeah. You can.
How so?
So on the top, everything has a common denominator of 2. So you can make it 7 radical 3 plus 12 minus 6 pi over 3. And then on the outside, it could be 2r squared.
That's true. You can. Yep. That's another way of expressing that. Yep. So Emmett's saying this is 7 radical 3 plus 12 minus 6 pi all over 3. And this multiplied by 2r squared. Okay? That's another, that either one of those answers, okay, are perfectly fine. Okay? So that right there in a nutshell is the solution to that enrichment problem. And which I think everyone here, had the right tools to go about it. You just needed to sit down and think about it and organize it. Did anyone here try to solve it by breaking up the areas like I had shown here today?
No.
All right, so that's that problem there. I'm going to stop recording.